stars. So I am involved since the beginning of Virgo in some hardware connected to suspensions, to thermal noise of payloads, to control of payloads, and some topics also related to the operation of the interferometer. I reshuffled a bit the presentation after Michele's talk yesterday, so that I'm showing here what he had shown and what probably will be taken again in consideration by Jan. The framework of third generation detectors will pass through the proper choice of the site. Here I'm showing one, let's say, very highly seismic day in Virgo. Indeed, this is typically a little bit lower, and in LIGO it is typically even lower than this. But this to show that certainly at present we have to deal with things which are in this level, much worse, maybe 100 times or at least 50 times worse with respect to what we expect in the underground. And this is what we will still have for the next 15 years. So I was also gathering questions and comments by people through these few days here, and some of the comments was related to resonant bars, which was their sensitivity, their bandwidth at the time when they were active. I mentioned the bandwidth of some tens of hertz, at most 50 hertz. One of the other issues was which was the maximum sensitivity of those devices. This is one of those. Nautilus was installed in laboratory, INFN laboratory of Frascati, and previously at CERN, of course. I used to work with these devices here, electromechanical resonant transducers for these devices before being involved since 1994 in Virgo. And in 2005, we abandoned essentially these detectors because, you see, the bandwidth allowed by interferometers was much larger, and also sensitivity. So this is what makes the interferometers very long. So one of the main characteristics is the length of these machines. And here I summarize things which are very well known for the students, but I was told to take care also of some comments dedicated to non-specialists, but now I understand that they are somehow very advanced to some extent. But this machine is a machine that provides at the output a power which is proportional to the amplitude of the wave, different with respect to real telescopes, electromagnetic telescopes. And this has to be taken into account, as well as the fact that the amplitude phases the inverse of the distance of the source. And that means that, of course, that making an improvement in sensitivity to the amplitude of the wave improves the number of detectable sources by the cubic of this cube power of this sensitivity improvement. Another point is that we detect power, and then, of course, we are affected by all the typical noises related to power fluctuations and so on, which had been properly commented in optics-wise talks. This is what we have today. This is what we expect to be the spectrum of these waves, and you see, we are working here. But as we want to go deeper, we would like to go deeper in the universe, in the space-time. We have to approach the space, or to use elements staying in the sky, in the space, to provide, for instance, deeper information to use, for instance, pulsar timing, and also, of course, some dream on cosmologic era through other kinds of detection. But here, we are here. Let's focus on this. Acoustic bandwidth, this is what we can afford staying on the ground. And my work was mainly related, since the mirrors, the test masses are not really on the ground, my work was mainly related to these two topics, which actually would completely cancel the effect of any gravitational wave detectable through an instrument which has the masses seated on the ground. This is the scheme we have today, and the network we are approaching to have in the next, say, 10, 15 years. Nowadays, the network is really made by 4 interferometers, but 3 of them are the effective ones in producing scientific data. And let me remark just that this is only 3 kilometer Virgo with respect to 4 kilometer, almost co-aligned LIGO. There is also to be mentioned, of course, CAGRA, which is being commissioned in these days, in these months, and which will, of course, work soon, probably joining O3, and LIGO India, which will be a copy of or inspired, let's say, to present technology of advanced LIGO. Let's approach the problem of suspensions. Suspensions in general is a word which has several folds, several meanings, we will see. But let me say that at least staying on the ground, but also in the underground, depending upon the seasonal period, on the season, we have more or less microseismic activity. That means that the wave of the sea continuously are continuously impinging on the reef, on the coast. And you see there are 2 typical peaks depending on how this sea is large. For instance, we know that Mediterranean is much smaller than this is Virgo site. So we see very clearly the peak around 300 millihertz, between 300 and 500 millihertz. That may change a lot, more than factor 10, you see. And this is the typical Atlantic peak. Different number of days of this, the percentile of the, so we have 5% of the year with a very small, we have, okay, this is essentially the percentage. And this is a good model of the seas. In average, is 10 to minus 9 at 10 hertz. Well, we need a big suppression of this. Let me compare an old result. Of course, we understand that our bandwidth starts from 10 hertz, but this noise contaminates all the sensors we are using to control the interferometer. So this is important. This is a peak of the noise into the Kamioka mine, okay? With respect to Virgo, just to compare a result of a ground interferometer with respect to underground interferometer, okay, in different seasons. So we might have this or this. Okay. There are open topics on this. We have a model we typically use, which is 10 to the minus 7 meter at 1 hertz, then fading as the square power of the frequency. And so, okay, this is made by using a geophone located in the underground of the Kamioka mine, site of, actually this was the site of Clio, the pilot experiment many years ago. Not really the site of Kagra, but nearby, I mean, something similar. These two are Virgo in different conditions, different weather conditions. This is the spectral density of displacement. Okay, so in order to construct a displacement here with the geophone, which is a measurement of speed, I have to, of course, divide by omega. And while this is taken with using a seismometer, standard, Guralp, I think, Guralp seismometer. Yes, meters per root of hertz. It is, sorry, many labels are too small. I realize low quality. But for the students, what the sensitivity is of an interferometer, we have said that an interferometer is characterized by the noise that limit our capability of using it to detect very small ripples in the space-time. And due to the noise which affects all the part of the interferometer, which could be moderate but also measured to some extent and projected in terms of H or strain, we can characterize the interferometer with this curve, experimental curve. So this is what we somehow expect from the model, and this is what we can reach, for instance, with our measurements. Okay, and we complain when we are not able to reach our expectation according to the model, because it means that there is some further noise which is affecting us. One good point of these detectors of Virgo, but also of LIGO nowadays, it is that they are meant to be limited only by intrinsic noise. That means shot noise here, and we know it was explained, this slope of the shot noise as due to the pole of the cavity, resonant cavity on the arms. In Virgo we have, of course, also the pole as in LIGO, because we have the finesse 450 of the cavity, and we have thermal noise related to these bodies, because test masses are not they have a volume, they have a temperature, so that they fluctuate and produce a noise which is located around here, let me say a little bit smaller than this limit here according to the model. But we still, in this example here, we see that there is something else. This is what we call sometimes technical noise. The system is not reaching its nominal capability. And here we have also, normally here, this is the region where we have a tail of the controls. Controls indeed, most of the controls are made at very low frequency. Some of them, especially locking controls, can reach the detection bandwidth, but then they are subtracted, of course. So they don't count. This is the real sensitivity. But if we have technical noise in the controls, of course, that might produce some effect here that prevents us of reaching the nominal expected curve. This is typical if you have, for instance, a driver, actuator driver, which is producing noise, and this curve will go up. Okay. So again, for the students, if we have a very simple Michelson, we wouldn't, of course, we would need again controls, but to a much lesser demanding extent. But if we have cavities, this is a very critical point, because the response is good only here. So we need a very good control system that allows us to sit here, fine-tune and locate our operation point. So sorry for this slide. Maybe it's stupid, but this is harmonic oscillator provided by a pendulum, very simple pendulum with no bending points, nothing is here. And that is the response, of course. This is in terms of time domain. This is in the frequency domain. Okay. We apply normally the Fourier representation. I say this because this, according to this formula, provides a slope which will be shown later in a plot, which is as known a slope that goes simply as the square power of frequency, and at the omega naught here we have a jump in the phase by 180 degrees. We will see it. This is what the spring is, with a dashpot in the simplest case of a spring which has no mass. In reality, this doesn't exist, of course, but we can make the exercise. You have made the exercise, of course. And there are two cases: friction, which is provided by the dashpot, or let me say, by the internal process into the spring. This doesn't tell much, but we have an important parameter here, which was mentioned by Yuri as the height of the Lorentzian, provided by these formulas, which represent pi times the number of cycles the oscillator undergoes before having a reduction of the amplitude to 1 over E, which is maybe 34%, I don't remember. Well, let's imagine now we have, this is nothing new, so we should fly on those, but, sorry. Let's imagine now we have a more complex system, but still very simple, and which is in the textbooks. This is just to show that what it is very important is the ratio, which is the displacement transfer function. Okay, in this more complete case, in which we consider, I'm talking about those systems because they are the base of suspension system, essentially. So I will use a lot these ones without formulas. So these are the only ones I'm showing. But let me say that we have here a component which is important here, that is the ratio between the mass of the spring and the mass which is attached, an effective mass which is defined here, which depends by both the masses, of course. This is normally reported in the textbooks. But let me say that this flattening effect, asymptotic effect of the displacement transfer function is seen here in the displacement transfer function, but it is not seen in the really called transfer function, which is the response with respect to the applied force. Okay, we will see. We will exploit this in the context of our oscillators a bit. Exploit just. I mean, I will show how it is exploited. But this is double oscillator, very simple. It is used to investigate things, and also in the paper following what was mentioned by Yuri yesterday, Cullen Walton paper 1951 and subsequent 1952 also, it is explained how to compute the thermal noise also of this system, even in presence of many modes. In principle, it is possible, according to the fluctuation dissipation theorem, but we are now interested only in the attenuation provided by this. With one oscillator, we can do this, and with two oscillators, we have a big advantage. You see, in order to have the same with a single oscillator, we should have a very, very long oscillator. Normally, I bring to the students, but to the high school students, not to the university students, some pendulum which has one or more masses attached, and then I shake it at the top. And this is very successful. They understand suddenly how downstream it doesn't move. Of course, you have to take care to move at always at the right frequency. So if we put several stages, we might have a very good attenuation here, which is what this is how Virgo super attenuator was conceived. Adalberto Giazzotto designed an interferometer which had to be had to be unaffected by external disturbances. When we speak about external disturbances, it's not a big one. It's a standard background of seismic, nothing else. This is very important. What does really suspension mean? In the past years, yes. Yes. That's a very good question. Of course, they are sustained by the background of noise, so they will be the RMS corresponding to this phenomenon you're mentioning will make the suspension, the mirror move, of course. So, but we need a damping system of these peaks. We call it inertial damping. So, of course, it requires inertial damping. It requires also control. Passive attenuation system is not free from the usage of controls. It requires also controls like the active system. Different kind of controls, of course, but that's a proper question. What suspension is? So in LIGO community, at least until I delivered some talk, speaking and trying to explain, in LIGO community, suspension was really the suspension of the test mass. Okay, that means the way we have to hang a test mass, preventing the suspension system, these wires or whatever system we want to use, to spoil the thermal noise of the suspension. So we need a very low dissipative mechanics there, very high Qs and so on. So we have to build a good suspension system. But in Virgo, which was conceived as a passive system made of several stages, normally seismic isolation builders and designers thought that the suspension was something starting from the ground, down, up and down stream to the mirror. So something much more complex. So I tried to better clarify this point by calling it last stage suspension system, the so-called payload, the last part, and super attenuator, which was called originally, it was originally the name of the suspension, but in the mind of some people was the whole, and I clearly separated, even though it is quite clear that the two things must be treated together in order to really analyze the response of the system. So I introduced overall suspension system that makes everybody in agreement on this. In Kagra community, there is something, it started later on, but the system is quite similar to Virgo. Absolutely the same from the conceptual point of view, but they called vibration isolation system. I share this, I find it very proper. And then down there is the payload, like in Virgo, which in that case is a cryogenic payload. This is interesting. When people come to the Virgo site, they see a structure in the main building, which seems to be a dummy, a sculpture inspired to the conceptual idea which are underlying the super attenuator. Indeed, that was a real prototype because it was made of gas boxes, these volumes here, the gas pots with inside there was some pipe, a small pipe, and letting the gas be regulated. Then the two wires suspending one, the gas. That one is attached to the body, okay, the upper one. And the other one is attached to the volume that is allowed to compress the gas, okay. So it is not the wire that goes through, but there are two wires. These are one wire, another, another. So it works also as a vertical suspension system. That was the first exercise, but then there were a lot of problems. Of course, it was tested with 400 kilograms here. There were troubles in letting the temperature be stable. You understand all problems connected with usage of gas instead of much modern material. But somehow it was demonstrated that it worked. Then this is the history, again for the students. All of you know this. Blade system, it is also used a lot in LIGO, of course. We use pre-bended blades made of maraging, which is a special ultra high resistance steel. So it means that the elastic limit is very extended, and it is used in the technology for making the planes, or well known for golf usage. So, but it's not a material so easy to be used. For instance, it's not usable in cryogenics. This is a problem because we would use. The good point of maraging, it is the fact that it is almost free from creep. So no non-linear effects let the blade go slightly down and down and down with the time being. Okay, so it keeps, but it's a bit fragile under humidity, for instance, because the hydrogen molecules might get inside the material. All the metals normally absorb hydrogen or deuterium or other gases, and then that makes this kind of steel very fragile. Well, so it is coated, certainly it's treated, thermally treated and coated. And this is how the standard element of the super attenuator nowadays look like. This is the body, roughly 100 kilograms weight. The upper wire, it is fixed to the body and goes to the upper filter. And we have another filter which is essentially fixed on the tips of these blades here, whose number can change, okay, dependently on the weight. Have a look of those small things which are attached here. They are simply meant to damp. They are vertical dampers of flexural mode of the blade. So this is simply a kind of rubber with a small weight, few hundred grams, maybe 200 grams, or lesser, 100 grams, and they prevent the blade to have a node here. Okay, normally a spring like this would have 1.4 hertz, okay, of frequency, so not so good for having good. I think there is a hole which is made, of course, before the coating, and then a nut. Very simple. That is very effective indeed. Yes, of course. Normally, they are made to, I don't know how many kilograms, but normally you have to consider that on this, dependently on the height, if that is the first or the last, but up to 1 ton can be. So in the case of 1 ton, you have all the filter, plenty of blades. Once you go down, you have, and the last one, maybe you have only 4 blades. So no creep, this is the yellow, important. No creep, compact springs normally this is very compact. In order to have 1.4 hertz with a spring like this, you need something which has a given height, so how to construct it. So the essential here, it is that this is maybe 35 centimeter, 40 centimeter at most. And we have a small fishing rod here. Fishing rod is an interesting system, which is meant to adjust the position of these blades. But these blades are very rigid in this situation. In such a situation, this fishing rod would never have any effect here, you understand? But indeed it has. It has it, because the filter has a much lower frequency indeed, thanks to the anti-spring effect. Anti-spring effect is clearly explained here with at a glance. I mean, there is not the theory here, but it's very simple. When you have magnets with plus, which are forced to sit facing one each other, like here, of course we experience a force which is perpendicular, like this, okay? This is when it is balanced, no vertical vibration is acting on the filter, and this is when you attach some more weight, or you let the spring oscillate, and this force tells the system, you stay more comfortable far away from the center. So equivalently, we can say that the frequency gets lower, okay? Because it's the same of adding a negative spring here. Okay, so that pulls away. And we reach a frequency which is 0.3, very low. That's a good point for us, because we want to move those peaks at low frequency in order to have more gain in the attenuation, sorry. Inverted pendulum, it's another topic. This is a Virgo inverted pendulum, but also a Kagra inverted pendulum, same concept, identical. And by the way, Kagra is a different kind of anti-spring that will be explained by Kagra colleagues, but the concept basically the same, which are not magnetic, purely geometric, more elegant somehow. But let me show here, you know the metronomus is a very well-known system to provide the time for the players. Okay. You have the mass here. By rising up this mass, you may lower the frequency. Okay. In reality, so according to this expression, which is well known, adding, okay, to the chain of filter an inverted pendulum, of course, produces this attenuation, because the first inverted pendulum has a very low frequency. But we will see how we use the inverted pendulum, not simply as a filter. Anyway, the system, as the frequency becomes very low, becomes also very soft, very gentle. We can apply a small force to arrange its position. And we want to apply very small forces on these detectors, because anytime you apply a correction, there is also a noise, which is technical noise, sorry for the word, connected to this correction, that makes worse the system. So the lesser is the noise we apply to keep the system, the better normally is the system. So normally, thanks to this inverted pendulum, we can reach a very low frequency, which is equivalent to a very long, purely gravitational pendulum. Okay, where is the restoring force? Restoring force is provided by the joint here. Okay, so we have a given shaft that goes up, but a thinner part, a hinge here, that allows you to go up and down. We use it as a pre-isolator. If we have two of these and we add joints up and down, we have a plate that moves horizontally, okay? And the frequency might be tuned. There is a phenomenon which is called percussion point of the force. Would like not to go through this, but this is anti-spring effect, but you can understand easily that there must exist a frequency at low frequency. The system flexure point is here and the percussion point is here. But it must exist a frequency when this point goes a little bit down or farther from the flex point, because you are applying at high frequency the vibration, and then suppose you are applying a vibration on the ground, and that will we try to turn to flex this point here. Okay. And by regulating the mass, adjusting the mass of the legs with respect to the mass which is on the top, one can tune some parameters. And we can do it by putting here counterbalances. Okay, understand? This point goes down, but we add some load here, and it goes up again. It's a very well-known game. So all the inverted pendulum have, normally you don't see the hinge because there is some further mechanics that surrounds it and which holds a big mass under the flexure point. So this is how the suspension looks like nowadays, and how the payload looks like. This is in the assembling room. So these shafts here are just meant for assembling purposes, and to bring inside through this hole the payload and attach it. It's a single suspension, single point suspension. We have a cage which surrounds the mirror, actuation cage. More importantly, let me stress that there are baffles which are attached to this actuation cage. So the baffles of Virgo are essentially suspended to this filter, the body of this filter here. So we have 1, 2, 3, 4, 5 filter before, okay? So the stray light we have around the payload, the remnant of this stray light will be recycled by this very good baffle, which indeed doesn't reflect anything, but a residual will be reflected, but with a very, very small displacement. So almost, we have never seen with these baffles any diffused light effect, indeed, connected to the motion of this system. There is the marionette, which is the steering body, what it is called in LIGO penultimate mass, which is meant to orientate the test mass, because test masses are mirrors in reality. Yes, essentially super attenuator. This is, sorry, I don't like to say good things about our system, but indeed that is a very good point. The basics of this system is the same. We have updated the payload nowadays. I will explain how we have updated it. But these filters are really the same. The conception, the pendulum is the same. Pendulum legs here are this gray stuff here. We can see one, and hardly we can see the second, because the green is the ground mechanics, which is brought upwards up to the actuator stage on the top. So indeed, we control the system not from the ground by acting on a possible imaginary inertial plate, which could be here at this level somewhere, but we are controlling the system from the top. So from this point of view, the system transfer function to the mirror will see a zero pole pair related to the inverted pendulum. it doesn't see the attenuation of the inverter. That's clear, must be clear. So the microseism goes from the ground upwards through the green stuff, and if the sensor is affected by the microseism, it will partially reinject it. Of course, we can play with the digital filters in order to prevent it, but nothing more. Indeed, we can do something more, but I will show how. Of course. Okay, I show you vacuum chamber in this system. Sorry, but they are not shown. There are two vacuum levels here. One is the level of the optics, which reaches indeed, you see, we call this the pot, this pot. Indeed, here there is a conductance pipe which allows to keep two different vacuum regimes in the region where the super attenuator elements are located with respect to the region where the optics is maintained, because this kind of vacuum must be better. Everything is under vacuum, that's clear. But the real experimental space where the optics is accommodated is this one, from this gray stuff here, which is made of two different parts which are then connected. And there is a small hole which is not, it doesn't appear here, but it's very small, few millimeters. We have a single wire that goes downstream. Essentially, all this part here, it is what in CAGRA is in cryogenics. It's into the cryogenics. Because also in CAGRA there is a vertical stage into the cryogenics. The modification, it was, last modification was to separate the vacuum here and not here. But this was, I will explain why we did it. Anyway, everything is conceptually the same. Kazuhiro, are you happy with this? Are you, I mean, did I answer to your question? To what aspect did you impact? Doesn't change, which is 280 dBs at 10 Hertz for the horizontal. That means 14 zeros before 1. So a very strong attenuation. And that is the question which was raised by some of you yesterday, which was concerning how can we test a system that provides 280 dBs in reality and before constructing. Nobody tested. But of course, we could test stage by stage and combine the transfer function. Okay, this measurement here, which is wrong here, because it should not go up. That is a mistake due to the seismometer at low frequency. The signal here is good up to here, maybe. But anyway, what matters here is this one. We measured stage by stage and combine in order to have an experimental transfer function. Of course, we could construct with MATLAB, with some program, the theoretical one. So we had the theory, obvious theory, but some theory. Everything is a theory. Also, a scale where you weigh your body. You weigh your body. That there is a theory that tells how to calibrate the spring. Okay. There is a very simple theory and an experiment, a construction. Then we measured this transfer function once we had the interferometer. And it was exactly that, of course, by injecting lines at the top and looking at the interferometer response. And we wanted a good... Yes. Yes, from the top. We measured the transfer function, because essentially the attenuation is provided by the lumped pendulum chain, by the cascade of pendulum. You can do it. There is a paper, very trivial, but maybe You can do it in Kagra, definitely. We use the frequency at 35 hertz, roughly. What else? Nothing. Modification, passing from Virgo to advanced Virgo. We improved a lot the payload. We made it simpler. This is just a sketch, so sorry, made with PowerPoint, but it explains very clearly. Previously, we used a reaction mass with its center of mass coincident with that of the test mass, okay? We had monolithic suspensions. It must be stressed. We had monolithic suspensions in 2010. That means fused silica fibers here, 180, something 180 or 200 micrometers thick, reaching the mirror, and going to a mass which unfortunately different with respect to LIGO. It was made of, it is still nowadays made of steel. So we might complain a bit about the clamping of these wires, of these fibers here, but at this level they were, say, there was hydroxide catalysis bonding standard, so I think performance of the thermal noise was not so bad, also in Virgo Plus. But we had reaction mass, and reaction mass produces, you know, that we wanted to lock the system, so we needed an easy way to lock. We liked a lot the idea of reaction mass, which was in Virgo since the beginning. But you see, this is a double pendulum, which has a mechanical node here, which essentially this point doesn't move when you have a differential motion, okay? But to some extent, you might have, if you have very different suspension for the reaction mass and for the mirror, you have a leakage of energy, an energy which is, it passes from the movement of the reaction mass, which is through steel wires, upwards to the marionette. It is filtered by this, but anyway, the thermal noise peak due to the presence of steel suspension of the reaction mass was nominally seen in the thermal noise curve of Virgo. And moreover, it makes the control a little bit more difficult. Lock acquisition is trivial, but then low noise control, that means moving as much as possible the force upwards, that is more difficult. If you have two pendulums and you control this stage here, you have two pendulums lying downstream. So in this system, the new one, we have a big cage. We actuate from the cage to both places, the mirror and the steering stage. This is a part of the last filter of the chain. And you see the black point, the white point here that goes up and down. That is the suspension point of the payload. It is attached to the tips of these blades that go up and down. And this wire here connects the system, as it used to do before, to the upper filter. So, that is the essential. What matters for the thermal noise we mentioned yesterday here? So first of all, we reduced the number of stages that attenuate the actuation point. We passed from 8 horizontal and 6 vertical to 6 horizontal, 5 vertical. Nothing changed. Why? Because, of course, the actuation used to be done on the mirror through a stage that was suspended, but now this stage is suspended not here, but even upwards, at this level here, from the big case containing the last filter. Okay, so we have 2 stages less, you understand, from 8 to 6. This must be clear. Raise questions if you don't understand. Control on the marionette, on the penultimate stage, is the same as it used to be in the past. Okay. Why we did this? Because we needed to house the baffles, which are now suspended, as I said, and also thermal compensation plate. Differently with respect to LIGO, we have 18 centimeters between the test mass and the compensation plate. According to the estimate, this is better. This is not that speculative point, not a speculation, this is practical. This is to show an effect which is not easily seen. You know what cross correlation. We have spoken about spectrum and power spectrum yesterday, power spectrum density. But if I have a process which is not linear, and I have, for instance, a body which is here, it was a baffle, you see, suspended by means of some wires, okay? This baffle was located into the pipe, near the payload, okay? And exactly in between the last mirror, after the beam splitter, in between the beam splitter and the detection bench, okay? So a very critical point. We have dark there, the dark fringe. Nevertheless, okay, this baffle, which used to have a frequency, I don't remember how much, maybe 2 hertz something, or 1 hertz, produced a Q which was rather high, the Q of steel wires suspending this disk. Okay, this disk was suspended before the detection bench, in between, close to the payload, okay, and it used to vibrate with this Q, so very big peak. And it produces a noise in terms of H, which was modeled. You see, here it is written, according to several hypotheses and following this equation, which is typical of an up conversion process. If you assume a Q of 10 or 100 or 1000, you pass from one of those curves to the other, and closer to the sensitivity. And if the Q was maybe 10,000, we would have seen here a bump, even though the process, it was at 1 hertz, okay? So it was enough, in this case, to go inside and put some magnets here that allow, by means of eddy current damping of this oscillation, to pass from 1000 to 3. And then it goes down, because the curve which assumes 3 is this one. So this is a projection made by means of an estimate of diffused light projected through this kind of process and producing this. So after that, we understood that we had to suspend the baffles. So this is why we struggled a lot to this extent. Consider that baffles are also sitting on the ground. When there is microseism, the vacuum chamber vibrates and follows the macroseism and recycles inside the interferometer. Especially, this is the dark fringe side. Of course, very harmful to have this effect. And on this plot here, I show the optical levers, because this is a big advantage I think we have in Virgo. Actually, we need this system, because the single suspension point, because this wire ends up here. Indeed, it arrives to the center, very close to the center of mass, maybe 100 micrometers close. Not simple to balance this system. It's a body which is maybe 100 kilograms, and you put 2 grams, and you see a tilt. This to give you the idea. Okay, of course there are motors to do this, even remotely. But when you assemble, you don't see anything, because there is the airflow. Everything moves. You can imagine the switch, which was mentioned by him. What would cause here with such a flight? This is really a tremendous floating, a real payload. So we use optical levers impinging somewhere, and 3 optical levers allow to have a good range of control up to plus minus 6 milliradian, very large. So when you set up the system, you need a recovery system that is like the factory of water for humans. If it was possible having a factor of water. So imagine how precious is a control system which is flexible with respect, and with high dynamics with respect to movement. The node, we eliminated the node here, but it appeared here clearly, because this is a physical pendulum where one pendulum is the whole body, okay, and the other pendulum is a double pendulum. So we moved the node here, but from the point of view of controlling, this is in any case a big advantage. Basics of optical levels for the students. Trivial optics from the textbook, maybe don't care, but I will leave the transparencies. We have said once you have an impinging ray here and you tilt by delta, you see twice that angle reflected, okay? And you can also see what is the response to a translation of this mirror. And you have some formulas which you can even port in the simplest case of a plane through the matrix representation. And so this is the reflected light, reflected beam, okay, which is here. Then you apply movement to the mirror, and then it goes translated and also deviated by a given angle. And this is a lens. What is a lens? Simply a hole, okay? The simplest lens is a hole, but this is something better than a hole. We don't want to use a hole because we want aperture, okay? So we have a 2-inch lens. That is the aperture of our system. It is not just few millimeters of sensor. You understand? The plus minus 6 milliradian, where they come from. And this is how these two coordinates are transferred on the sensor by means of a translation from the reflecting point to the lens, and then from the lens to onto the sensor. Sorry, this is a bit boring, maybe, but you have a response here, and you see two components, one which depends on the angle and other depends on translation, and you see I have specific important points here, which are the focal. Sorry, also this is too trivial. Maybe this is explained maybe at the first year. It's 1 over f equal to 1 over p plus 1 over q. Basic rule of a lens. So essentially you see that if you stay on the focal plane, if you locate your sensor on the focal plane, you are sensing only the angle of the mirror. If you are sensing on the image plane, you sense only the translation. So if you have a suitable adjustment slide system with 4 degrees of freedom, one also to arrange, you need the gonio also to arrange, of course, properly the plane. But if you have a proper adjusting system with micrometric precision, you might have an extraordinary decoupling of translation with respect extraordinary. 0.2%, 0.1%, it's very good. Then you understand that you apply a control filter like this, click. You don't see coupling with other degrees of freedom. It's very simple to assemble a system of such a kind and to drive it to the lock. Then there will be a refinement, but that is the philosophy. This is what we have talked. Why removing the reaction mass? To simplify, in order to simplify the control, you see, you can control through the marionette. Through the marionette you have 2 stages. So you have the green, very simple. Twice, this is not moduled, so this is unfolded. You see the 2 steps, 180 degrees per resonance. This is, you know this, no? This is real and imaginary part of the transfer function. You apply a force to the marionette, which is the upper stage, in case of LIGO penultimate mass, and you measure the response at the level of the mirror. So you can compute the 2 things. Of course, when you actuate directly on the mirror, since that is the second stage, you will see a slope that goes according to the second power inverse of the frequency, which is omega at -2. And then you see a pole zero couple here. You must, because when you shake the mirror, you have a reaction on the marionette that goes on the other side, or on your side, but it has a freedom. Sorry, very trivial. Sorry. And this is the whole system. That's how it works. We have a super attenuator and a payload. Similarly, probably to Cagra, we have the top stage of the super attenuator is controlled by means of position and acceleration sensors. Position means with respect to the ground, then subject to the microsystem. Acceleration means with respect to the stars. The bottom is controlled with respect to the ground because, but it is not meant to stay always controlled. Just to damp big oscillations, we can recover applying a force at the bottom of the chain. And this is the payload. We control 6 degrees of freedom and so on and so on. So this is the divide et impera. It was Roman emperor Julius Caesar who invented this, because diagonalization and hierarchical control is the keyword here. Since the mechanics is very well constructed, just a quick look on the optical lever. Sometimes people are concerned by the noise of these optical levers, capability of reproducing the lock after interruption. Of course, they are seated on the ground, on the base of the tower. They are almost industrial stuff. Not too industrial. Indeed, they are not industrial. They are simply well designed. This is why they are very simple. Over 50 days, okay, so with a lot of drifts on the system. Also the water that gets into the soil makes the tower change a bit, these things, temperature, there are many effects. You see that the recovered lock, it is within 30 microradians. So that means, since in order to catch the whole of the interferometer, you need a precision of few tenths of microradians, it means it does the work. This system does the work. Of course, it's well covered. There is no fluctuation of refraction index, these things, but that is related to the signal. This is related to the stability allowed by this system. And so this is for us very useful nowadays. This is LIGO. And of course, I'm not commenting the many suspensions. There is a beautiful poster outside. But moreover, I'm not expert, but I know very well how the scheme works, because with Norna Robertson, we collaborated in writing together a chapter on these two things, Virgo and LIGO. And you see, what I notice at a glance, it is the beauty of this frog. Very stable, very large and stable. I like it a lot. But the concept is very different. There is a pre-isolator here, active control here. So there are sensor and subtraction of noise, also at this level. Then there is a couple of these stages, an overall of 7 stages, if I'm not wrong, active. And after the active, it means that there are sensors on boards, and they are capable of subtracting just by activating it, the microsystem is subtracted significantly. And then there is the passive system, which is hung to this, which is this one. well known by everybody. So this is the series. All the stuff here is in series. This is what we call marionette. In case of LIGO, there is a reaction mass for the marionette. Two simple pendulum facing each other. One particular case, it is the small distance between the thermal compensation plate, because the reaction mass is also a compensation plate. In this case, with respect to Virgo, but essentially it's a very sophisticated work. This is the overall stage, you see, exactly corresponding to the sketch. What I personally like a lot is the material here of the penultimate stage. Of course, DC regulation, there are no motors on board here to adjust the angle, because the work is done upwards with the system. So to that extent, we understand we have to house motors and DC drivers. It's difficult to build a piece made of fused silica, which has all the things inside, but we're thinking to something. We probably will do some experiment. So this is explained outside, so I would like to jump, but you see, very stable. I like a lot, compact. Indeed, not so compact. So see, it's the aspect ratio that matters here, not because, of course, this is enormous also. It's very tall, but the aspect ratio is like that. And this is what was provided. You see, if you project on this, of course, okay, this is very important. This is the ground at LIGO, which was like this during this experiment, test experiment. Thanks to simply to the active suppression, you see this neat effect from the black to the blue. Very effective, very nice. Consider the peak they have. It's essentially ocean peak here. It's not the Mediterranean peak at 350 millihertz. And this is the effect of the passive, adding to this the passive filtering thanks to the quad. The suspension point is the suspension, say, from where the passive system, the quad, let's say, starts bottomwards in this case. In case of Virgo, it is in between the last filter and the payload. Unfortunately, the case of Virgo is related to a noise which is very high indeed. Sorry, in this case. But the attenuation is very impressive, of course, because we have a lot of filters at low frequency. But as he was saying, there are these peaks, and these peaks must be attenuated by means of inertial damping, taking into account the so-called acceleration, fixed stars in the sky. So CAGRA is the system, which is similar, same, essentially. It will be shown, commented probably by Koki and others. And there is need of chain mode damping. What does the inertial damping do in this context? Okay, this is the transfer function of the payload from the suspension point of the marionette. I have here a wire, then the marionette and the mirror. I shake this marionette, and I see what is the transmission of displacement to the mirror. Okay, but in reality, this is attached to a chain. So from that point, I should see, from the marionette and from the mirror, so I should see also the chain modes. If I apply the damping, the inertial damping to a chain, the transfer function becomes much smoother, you see. It becomes the dotted one. So it has a meaning. Again, transfer functions, sorry. From the suspension point to the marionette and to the mirror. This is experimental measurement. Of course, it fits what expected, but what it is important here, it is this shape, you see? We don't see big peaks. This is when the inertial damping is on. So we switch on the damping of the chain, and then we observe what the transfer function from the marionette to the mirror is. Clear? Okay, suppose that we were hanging our system to ground. Okay, if I start here, don't let me start, otherwise. So I hang the system on the ground. This is fixed, an infinite mass here. And I apply a force. Okay, that would be the transfer function, simple pendulum. In case of a damper system upwards, this is the situation, even better. Understand? So that, imagine I had a perfect platform, inertial platform, that allows me to have a inertial state of the suspension point. I would have something like this, but I have something very good, very simple here. Of course, I need a lot of damping upwards. It's not fully equivalent, but it gives the idea. Other advantages or other meaning of the inertial damping. Okay, acceleration. This is very, I think, interesting. Acceleration along Z. Z is our longitudinal degree of freedom beam. Okay, sorry, it's a bit of jargon. In this case, we can control the top stage just with position sensors, or with position sensors plus accelerometers. Look at the difference. Very impressive. This difference is due to the fact that all those peaks mentioned by him were influencing, of course, the movement of what is below. So accelerometers are very important for controlling the modes of a suspension, which pass a long chain of stages. I mean, design of the payload. I'm not sure if I can mention the open loop gain function, can I? Okay, it is, I try with words. Okay, it's a characteristic of what I can do on the system, a given system. So there is the information about the dynamics of the system, all the transfer functions we have mentioned. With my tools, my circuitry, my analogic or digital, doesn't matter, in order to reduce an error signal. Error signal is the variable I'm looking at, and I want to keep it steady. Okay? All of this is added and subtracted to the error signal in order to keep the system steady. So here there is embedded not only the filter I use to control the force. Suppose I want to stop, I don't know, somebody who is an oscillator, which is coming to me. If I use the wrong phase, of course, I will excite it more. It will fly away. But if I use the right phase, I will slow it down. Every time he comes on my side, I properly accompany to stop it. Okay. That is my filter. Okay. And the oscillator is the transfer function. The two things are here. If I want to change, okay, in this case, consider this pitch open loop gain function. So the control I apply to my system. You see that it doesn't control, this is 10 to the 0, it's 1. It means that here I'm not controlling anymore because the value is 0.3, 0.4 at 1 hertz, 2 hertz, sorry. It means that my bandwidth of control is from here to roughly this point here, with a small peak here just to stop one peak which was disturbing me, so I added something to correct. That means I want all the modes of the payload at low frequency, because otherwise, in order to control the system here, I have to apply more force and technical noise follow. And the nastiest peak I have is that of the differential arm. So the two differential plus, we call it, a bit of jargon, sorry. But it means two axes of the cavities are moving on the beam splitter in order to go away from the perfect contrast. That depends on the common movement of the two mirrors, but in opposite directions. Differential plus. This is most critical, you see, in our detectors. So if I try to confine all my system, all the frequencies of my system at low frequency, and I aim to have the number which is produced by LIGO as noise of the for monitoring this, which is a very good number. We have worse, indeed. If I put the two things together, it seems that with this payload, I can reach easily maybe advanced plus nominal angular noise, but of course there will be other technical noises. It's simply thanks to the mechanical design, nothing else. Now, optical levers are sitting on the ground, so we have a beautiful system which provides quasi-inertial state of the test masses, but then we have to drive this, then we have to use further position control systems which are seated on the ground. Problems, they are noisy, they don't have perfect electronics, but anyway, they work to align and to lock the system. Well, let's imagine that we pass from a situation in which we have position control with respect to inertial damping of the top stage, okay? If we have position control only, we have at the level of the mirror this kind of noise here. We apply the inertial damping, we go then here, this is the acceleration of top stage. We don't see much on the optical levers, okay? But if we divide by the ratio of these two things, we can easily deduce what is the real angle affecting my test mass. 2 nanoradians of RMS. And this is not thanks to the optical levers, clearly, because they are noisy. They are flattening everything. Thanks to the super attenuator. Is it clear? So the system roughly works. Say. Sorry. Now pictures, because you have to enjoy. So no comments. This is only a student who took a drawing of me. I was there, mounting something. This is a technician. This is some paper I could not read. I haven't finished, just to relax. This is to relax. In Dutch, so I don't understand anything, but I provided some pictures. This is, you see, beautiful cabling inside. There are 25 kilograms of cables inside, and they play a big role in the mechanics of the system. Fortunately, we have a modeling tool that also takes into account the mechanics of these wires, cables. This is beautiful. These are astonishing. I always wondered how it used to be before. They had been probably introduced by Riccardo De Salvo at the time when they were experimenting the single element, because he participated to the design of original design. Then it was modified, but the concept of the blade with this was provided by Riccardo probably. And also benches, beautiful optics is suspended, as in LIGO, of course, with different system, but concept is here that it is suspended through 3 wires, this injection bench, 3 wires going upwards to a kind of marionette, and then a super attenuator also there. And these things are not seated on the ground, as they look like. Indeed, this is a bench, an auxiliary bench provided by Nikef, which is meant to gather the peak off into the cavity, into a recycling cavity. Indeed, this bench is suspended by means of a single wire, and the signals are coming here by means of an optical fiber. And there is a tiny, very thin space here, maybe a few hundred microns of range. Yes, yes, that's very hot, maybe 50 degrees. Yeah, that was an issue. There is an electronics that nowadays, anyway, in the end works. The problem is that every time you open, you need to stabilize and so on, because it heats up in the vacuum a lot. So, because all the photodiodes are there, they wanted to have the electronics close. Yeah, to the cable. And also, we have only signals going up and in and out through optical fibers. You understand? All the sensors are inside together with their electronics, so we don't have other cables reaching this table. Yes, you see a flange, some box here. But this was just to say that this is also suspended. Also big benches, as you know, injection bench, very complex, suspended with gas springs like those which will be explained. This is not suspended. This is to amuse the during the mounting. You see, this is the marionette. Sorry for the lens which was used here. The shape appears to be long, but it is not long. There are 22 stops all around the payload. This is being constructed. It's not completed, of course. This is initial. This is, you see through the tent, you see here the ring heater and the mount of the ring heater, which will be then inserted. And we suffered of breakings, you know, old story I will not comment. It was a problem of dust bullets into the system. But this is well known by many people, but probably by you, young, not have a look to this. I hope there are not the voices, because this was a dummy mirror, first version, 2009. This is suspended through fibers, 22 kilograms, 180 micrometers thin. You don't see the fiber, of course. So glass is extremely robust, you see. It's very nice. Let's try to see. At the end, the scope, it was, of course, there are the stops that prevent the elongation be larger than the breaking maximum. So we are really trying to destroy. At a given point, we have a resonance, vertical resonance, boom. It's fantastic. You see excited the mode. This is 9 hertz or 11 hertz, I don't remember. Stop, and this is the final. Boom. So now it is, the mass, of course, is like LIGO, 43 kilograms. Same method, fibers are a bit thicker. And this is how, when this is assembled, there is a lot of further things, motorization of everything. We can motorize everything. Now, next payload, lesser motorization, because I hate it, especially if it is not needed. These are the coils, very small magnets, indeed 1.5 millimeter, aspect ratio squared, height 1.5, diameter 1.5. They are inserted in glass holders, of course. And of course you see here the famous polymer first contact, which is located on the mirror, then remove it. probably I'm finished or not. If I'm not, I can go on because this is beautiful what I have now. That was to relax, but this also to relax because Connor provided a beautiful sketch here, taking into account the fact that one thing is missing, that is the tilt measurement at the ground. And as we know, the tilt contaminates any kind of inertial sensor. So, but in LIGO they are happy because there is this device here, which was studied at Washington University and then installed by Krishna. And the idea it is to correct the sensor which is seated on the ground, subtracting the tilt, making such a sensor not sensitive to the tilt, and then feed forwarding for controlling purposes to the stage of suspension in LIGO. But in principle, the things can be similar things can be done also in Virgo. The fact that in Virgo we haven't this yet. Another fact it is that this kind of sensors, any kind of sensor below 100 millihertz, are very tracers, and sometimes they don't show coherence. You put two things here and they are not correlated. So indeed, the contamination was an old matter, and it was indeed the principle driving the design of the super attenuator. But then we didn't pursue towards the development of the sensor, even though several things had been done in Italy, but never leading to a result. But this effect, once the first measurements were done with the super attenuator prototype in Pisa, showed such an effect. That was reconstructed as a tilt sensed by the accelerometer on a platform. This is just a platform hung with wires, but by doing this effect, it tilts a bit and it produces a signal, which is in turn seen as a standard coupling with another degree of freedom, in this case, the tilt, zero pole here, always. And so it started somehow a dream at that time of an inertial platform. Actually, Adalberto Giazzotto used to think to this till he could. So that the legs of the inverted pendulum, I don't know in Kagura, but in Virgo, this is the counterweight. We had been talking about it, counterweight surrounding, but the legs is equipped with basic instrument piezoelectric stack there, and the spring which keeps the weight. The spring is a kind of washer here, which has a conic shape, so it works as a spring. So that makes the piezoelectric stack work around against a softer point, because there is the spring which counterbalance the overall weight. Okay, but we never use it because we don't have sensing for the tilt. We tested combining signals, but several developments are done in Virgo, but not yet an implementation beautiful like this. I follow it a bit because some colleagues of us are engaged in some device which is inspired by this, which is indeed meant for other purposes, but which in turn can be used also here. This is a balanced bar, which is whose angle is measured by means of an optical lever system coming from the top, and which has a very good performance. We have 10 to the minus 10. Sorry, but it is radians per square root of hertz. Sorry, this plot went, because I updated this. This is the one of the latest results of our system, which it works, of course, in feedback using an interferometer signal, and the optical lever, of course, is flattens the noise. So this is in loop and this is out of loop monitor signal, let's say, but it is affected by some noise. The new novel thing is that we have installed in Virgo now on the ground this system, so we might be able to do something similar, even though we don't have the active system, we don't have that big experience with feed-forwarding, but in principle that's a very performing device. We have 5 micrometers of distance in this system between suspension point and the center of mass of the bar. So big work from the mechanics point of view and also from the optics has been done. And this I'm free to announce it, but it's not an announcement. They are parallel developments. Also high energy physics are interested in tilt meters. At CERN they have developed such a device. It was driven by a mixed group. Sorry, I don't have here the whole list of names, but there is also, I think the main idea comes from the Russian scientist who is behind this, because in this case the reflection, first of all, this is very impressive because it is 40 by 40 centimeter. Reflection is on a liquid, and in Russia there is a long experience of tilt meters making use of liquids. Originally they were monitored by means of capacitive sensors, these levels. So, but this is an optical device, very nice indeed. But we have to explore this collaboration in the context of other things, for instance, exploration of low noise sites and so on. But it can turn to be useful also for us. Probably Jan will tell us something. But you see the impressive sensitivity. This is the microsystem peak, which is driven inside. Maybe the focal plane would be improved. Otherwise, it should not be there. Anyway, controls without tilt meters. We can control. If we don't have tilt meter, we have to grasp our head how to do. Actually, we can mix signals, position signals, and acceleration signals to have a quasi-inertial displacement, a hybrid virtual sensor here. We filter the two sensors by means of this neutral filtering. A low pass and a high pass gives 1. 1 in amplitude, it means 0 in phase, of course. They don't have to alter, of course, the combined sensors. What can we do by means of this? We can increase the slope, okay? For instance, we filter the position sensor in this way according to the blue. If we do this, unfortunately, the high pass, which filters the acceleration, goes up here. If I have tilt affecting the ground, I will contaminate a lot here. So this solution works when there is no wind, no tilt of the ground, and that can be used when there is beautiful weather, but it's a situation not so realistic, because normally if the wind produces microsysm through the sea, the two things go not in parallel, but almost. On the other side, I can, of course, do the opposite, okay? If there is big wind, maybe I can accept some microsysm, which is brought inside the system by this. The two things you see are very simple. This is the inverted pendulum. This is the PID corrector, digital filter. I apply. Set point doesn't matter here. But I have a seism which enters at the base, at the top of my inverted pendulum, and let it move. Okay, that responds, and then it is again sensed by the sensor, which is then in turn filtered. At the same time, acceleration is high-passed and then recombined here, giving rise to a signal, which is this one, which then is filtered again and feeds the corrector to keep the error signal. Unfortunately, there is also tilt noise, which also affects the system. So this is what I can do. It's simply applying a low pass and try to understand what to do, what is the better situation, the best situation I can afford. In practice, let me see what happens. What is the tilt we are talking about? I don't have any tilt meter there, so what can I do? Effectively, I can see what is the amount of tilt I'm injecting again through the controls, and this is the amount. You see it is very linked to the wind speed. I have 33 kilometers in average here. I have something 15 kilometers per hour here, almost 0 here. And you see how the low part, how the tilt is reconstructed tilt, okay? Reconstructed tilt, it means something like accelerometer signal, okay, minus LVDT, position signal, okay, omega square divided by G. This ratio gives you roughly, G is the gravity, this tilt. And you see, so in principle, I have a signal, I have a track. I could use this in feedback to the piezoelectric. In fact, it works. But for some reason, we don't have all the drivers for this piezo. Only one set of drivers, but we will probably implement it. You see, when it does a tilt here, that moves, sends it as an acceleration, and then correct it. But I can do something much cleverer. That is applying a different blending of acceleration and position through the cavity, okay? Because I have a very precious signal, that is the cavity lock. I can use that signal, which is very precise and isolated through the suspensions, so it is lesser affected by the microseism, because there are several stages. It's a bit reduced, maybe 1/5. It's a bit cleaned by means of the suspension. So if I do such a game, I can gain a lot indeed, because I can apply a filter which actually injects a bit of tilt on the central area, in that area, and I will substitute the position signal at the end. Sorry. I will simply reduce this microseism. Okay, this is the explanation. So I take the control signal, I apply the control signal instead of the position sensor, local position sensor here and here at the end. Then the cavities, the end mirrors will move according to the center as a big bench. So in Virgo must be seen as an optical bench 3x3, which is tangent in a point at the center. At the center, I can construct very clean sensors for the top stage control by combining all the signals, because the noise is common there. Microseism is common. Look at this. In this case, you see the end test mass follows exactly. We have a big speed of wind here, more than 40 kilometers per hour. And the end test mass follows the input test mass. It moves a lot up to few microns, 5 micrometers. Normally, that would not work. But since they move together, because I'm saying end. Oh, sorry, you should have told me earlier, sorry. But anyway, that makes the system very robust. And normally, this is the correction I would have had during this wind, while with the combined signals, I have the red here, you see? Very small correction. That means very good duty cycle. This is to show other things. Correct subtraction in the central building, subtraction of the microseism in quiet conditions, resistance to a quake. Normally, these quakes drive the system out of lock, normally. Far away, maybe about more than 6.8 or something. In this case, the sensitivity here was not so good, but 22 megaparsec. We didn't have the unlock. It could stand. And there are several other things and considerations. Sorry, I was too long because I wanted to be clearer for the youngs. And you see, seism and wind, they go roughly together. So only global control can manage this, not just mixing the signals. I'm ready.
More time in the afternoon if you
yes,
need to wrap up the discussion.
I can go deeper on these things, but no problems. I hope to, I was able to give a glance on this topic because it's practical, unfortunately, very practical. Questions? If there are no questions, I understand